let me introduce you to my collaborator. This is Fraczyk, that is Dixon instructor here, Jan Raimbault, Joe Chen, that was a graduate student of Danny Caligari, and Homin Lee, a graduate student at Indiana University. Oh, this thing doesn't work. So, okay, so like the main characters of this story are lattices. So let me explain more or less like the framework. So G is going to be a semi-simple real Lie group. X is a symmetric space, and I think about it as the group G being the group of isometries of that space. So maybe the simplest example would be when X is the hyperbolic plane, and G is the group of isometries of hyperbolic plane that is PSL2R. And for each of these Lie groups, there's like a corresponding hyperbolic symmetric space, and these always have like curvature, negative curvature between -1 and greater or equal than 0, you could say. So, and then there is like the concept of a lattice that is a discrete subgroup of this group, such that satisfy the following conditions. So one is that gamma is discrete. So this first thing should have been gamma is discrete, and the second condition is that the quotient has finite volume. So feel free to interrupt me if I say something wrong or that could clarify things. Okay. So here are like some pictures I found in the internet. So this corresponds to PSL2Z, that is a lattice in PSL2R, and this is like a fundamental domain that is like some subset that when you translate it by this group, like tiles the whole space X. Yeah, the last one there is related to a hyperbolic 3 manifold. So you could obtain it with a dodecahedron in 3-dimensional hyperbolic space, and you take reflections and you get this tiling. The group of reflections would correspond to this group gamma. And the second one is people having fun with hyperbolic plane. Okay. So yeah, so the more important like lattices for this talk are like called arithmetic lattices. So the definition is a bit complicated, and I just want to kind of give you 3 examples. So the first example is SLNZ and SLNR. So these groups are always defined by polynomial equations with coefficients in some extension of the rational numbers. So here is just like the case where k is the rational numbers, and the question is determinant equals to 1. And so this group is, well, it's non-trivial that there are solutions, like matrices of determinant 1 with integer coordinates, but it's also much more non-trivial the fact that they are like a lot of matrices like that in such a way that this SLNZ sits in SLNR as a lattice. So this is the first example. So second example would be just taking the same equation, but I just changed the field to q square root of 2, and then the group that you get is this SLNZ square root of 2, but this SLZ square root of 2 is not it's dense in R. So this is not a lattice in SLNR, but it's a lattice in SLNR times R. If you like apply the following trick, just you take the matrix, and send the matrix into the matrix and its conjugate. Okay. So the third example, I feel a bit masochist like putting this example, but it's quite important for us. It is okay. The field is q square root of 2 square root of 3, and then I look at this quadratic form x squared plus a y squared plus bc squared, where a, b are these numbers. You can put any numbers, but these numbers are chosen in such a way that when you look at the different embeddings of this field q square root of 2 in the complex number, so they correspond to just sending square root of 2 into square root of 2 or minus square root of 2, square root of 3 into plus square root of 3 or minus square root of 3, then always when you change one minus for a plus, then these numbers become positive. So when you apply like this conjugation trick, what will happen is that this, and if you look at the group of matrices that preserve this quadratic form, what will happen is that this quadratic form becomes positive. So this quadratic form, when you apply a Breuillard conjugation, is going to become positive, apart from the case in the identity, where it's like a form of degree 1 minus 1 minus 1. So this lattice kind of sits naturally in this product SO2 1 and SO3 times itself 3 times, just coming from the other 3 embeddings of this field. Okay, but you could project this lattice into SO21, and that's still a lattice. Are there any questions? So these are like the main characters. I'll tell you some history about these lattices. For example, the question of like the classification. So in dimension 2, there's just one symmetric space of this type that is hyperbolic plane. So like the lattices correspond to hyperbolic orbifolds or hyperbolic surfaces. And it's like well studied and understood that every surface has some like the number of possible hyperbolic metrics that you could put on it. But in H3, thanks to work of Mosto and especially due to Thornton, is well understood which 3 manifolds have a hyperbolic metric, and it's kind of like the generic manifold somehow has this hyperbolic metric that was quite surprising back in the 80s, I think. I'm not sure about the 5 years when this was discovered, but yeah. So one possible like answer for a classification would be like maybe to try to show that all these lattices come from arithmetic construction or this type of construction that I was showing before. So in 1977, Margulis showed that all lattices in groups, like for example, SLNR with n is greater or equal than 3, are arithmetic. So this corresponds where the symmetric space has oh nice. So where the symmetric space have not negative curvature. I mean, it contains some features of 0 curvature. And in around the 1990s, Kevin Corlett, which has an office here, proved the same for these like very complicated spaces, like quaternionic hyperbolic space and this other one that is much more complicated. So these things are like very high dimensional. So it's like one of like the open problems is to understand what are the lattices in SON1 when n is greater or equal than 4 that in hyperbolic 4 space and bigger. And maybe so there are examples where like these things are not arithmetic, and also this is complex hyperbolic space that is symmetric space that have curvature between -1 and -4, and still not know like the question of the arithmeticity. So yeah, so Margulis put this as like a question in one. So he wrote like a kind of survey. There's this book called Perspectives, and I don't remember. That is like kind of a survey of like important problems, and Margulis put this problem whether as one of the main problems, understanding whether like the lattices here are arithmetic. Okay, so that's part of the history, and yeah, so the questions are how this like for this talk are how these manifolds look like, and what's the topology, the geometry of these spaces, and something that you could ask is like about its topological invariance, like the Betti numbers, like the homology. So there's a lot of research in questions like the following. So you have a lattice, and then you look at subgroups of the lattice that have finite index in each other. So this corresponds to manifold taking finite covers of the manifold, and then try to understand why, like what's the growth of the homology. So this type of questions is connected to very deep things in number theory that, for example, Frank Calegari or Emerson could tell you a lot, much more than I can. There's very deep mathematics, I think, there. And but today I'm gonna like give a simple answer to that. So how do they look like? The answer is gonna be that they look fast. Okay. And the question is really how fast do they look? So I'm gonna start with two famous questions in one in number theory. So this is the Lehmer's problem. It's a question about polynomials. You take an irreducible polynomial. Oops. You take an irreducible polynomial, and then you look at all the roots of the polynomial. So these are the roots of the polynomial. This is 0, and this is the unit circle. And then you look at the roots that are outside the unit circle, take the absolute value and multiply it. Okay, and that's going to be a number that is going to be greater or equal than 1, of course. So if the polynomial is cyclotomic, all the roots are going to be in the unit circle, so it's going to be equal to 1. And the question is whether you can beat the 1, whether you can find some number bigger than 1 that multiplying all the absolute values of the numbers outside the unit circle is bigger than this. So here I wrote it in a bit of a different way by taking logs. Is like this thing that I defined here, log plus is just if the number in absolute value is greater than 1, is log of the absolute value, and if not, is equal to 0. So are there any questions? So far the best polynomial is this polynomial. Sometimes it's called Lemmer's polynomial, whose when you multiply all these numbers give you this. Yeah, so far no one has taken that. And this is related to a conjecture of Margulis regarding this X mod gammas. So just recall what X was, symmetric space, and gamma an arithmetic lattice. And then the question is whether there exists some constant epsilon x greater than 0, such that for all the arithmetic lattices, the systole, which is the shortest curve in the manifold is greater or equal than epsilon x. So here I have to assume that this is compact, or I will assume that this is compact, okay? So yeah, and these two problems are related, and the relation is that Lehmer's conjecture. So this is just, oh, sorry, this is just what was previously within the side. And so Lemmer's conjecture implies Margulis conjecture. And
what are you assuming about X?
X is just non-compact, it just come from a semi-simple Lie group, real semi-simple Lie group with no compact factors.
Oh, with arithmetic.
Yeah, the gamma was arithmetic. Gamma was arithmetic. Yeah. So this is not true if you don't assume that gamma is arithmetic. And so Lemmer's conjecture implies this Margulis conjecture. And more or less how this story goes is, so suppose just like I'm thinking about the case of SL2R, and I'm thinking about this lattice that I described before, or okay, let's take some matrix. So some element here corresponding to like a geodesic. So I have a geodesic, and this geodesic corresponds to some element of the group, and this matrix you can diagonalize. Okay, and then like simple like geometry exercise tells you that the length of this geodesic is actually the absolute value of this number alpha here. Okay, and so the minimal polynomial of this number alpha, when you apply this Lemmer's conjecture, you get that has to be like the length of this has to be bigger than this constant. Okay, so for example, when you take an arithmetic lattice in SL2R, like the one that I described, like the third example, the masochistic one. So always the characteristic polynomial has like this very nice fact that the roots, it just have two roots, one outside the unit circle, it has just two roots outside the unit circle, and the other, because when you apply Galois conjugate, they lie in a compact group. The conjugates of this lie in the unit circle. Okay, so it's very nice that you know can produce polynomials with exactly two roots outside the unit circle. Okay. Are there any questions? Yeah. Oh, yes. So, okay, I'll tell you about two things. An old lemma about like the geometry of these symmetric spaces, a new lemma related to this one. So this is called the Margulis lemma. So what the Margulis lemma is going to tell us that there are no two short curves that are close by. So the statement says that there exists some epsilon that is just depending on the Lie group, such that for any discrete group, if you take a point in the symmetric space, and this point is moved, and then you look at the set that move this point very few. So I'm taking my point X and looking at all the gammas that move this point less than epsilon, and then I take the group generated by this. Then this group is virtually solvable. Okay, so virtually solvable, that means there is a group of finite index that is solvable, which I just always think as abelian. In my experience. So in particular, there cannot be two short loops close by because the loops will correspond when you go to the universal covering, it correspond to a point that is moved very few by two disjoint, by two elements that don't commute. That's more or less the idea. So I'm gonna give a kind of proof of this, not really a proof, but like the idea of the proof. It's a very simple fact about matrices. The fact that if you take two matrices, these two matrices corresponding to the two loops, these two matrices corresponding to the two loops, and these two matrices are very close to the identity, then if you take a commutator that is this thing, a, b, a minus 1, b minus 1, which is what I would like to prove is 1, then this is much closer to the identity. So how would you prove this? The idea is just take commutators of commutators, and it's like a fight between like the fact that this group is discrete and like the power of the commutators. So that's the proof of this lemma, and but I'm going to tell you about a new lemma, and this lemma is what we call the arithmetic Margulis lemma. So the arithmetic Margulis lemma, what it says is the following. It's so here what changed. So gamma before was discrete, but now I'm going to assume it's an arithmetic lattice. Okay. And K is going to be the trace field that it was in our examples, square root Q square root of 2, Q square root of 3. And then what it says is that, yeah, there exists this epsilon such that the group of elements that move a point X, before it was epsilon, but now you have this gain here of multiplying by the degree of the trace field. Okay. Then it tells you that this group is virtually solvable. So geometrically, what this thing is saying is that if the degree of the trace field is very large, okay, then there are no two short loops nearby, but actually they have to be very far. And so it tells you a little bit that this, as I was saying, that these manifolds look fat, okay? And you have to remember here or know that in these manifolds, like balls grow exponentially. So there should be a lot of topology happening over here, or you know, there should be a lot of mass here. Are there any questions? Complaints? Yes.
Just the notation. So G is always a fixed reality group.
G is, yeah, yes.
So in the FLN, Z square root of 2, the square root of 2, you don't get any gain out of this, right? Because the G becomes double in size, right?
Yeah, exactly. Yes.
Okay.
Yeah. So to get like gain of this, what you need is a lot of compact factors.
Right, like in the other example.
Yes. Exactly. Yeah. And so I'm gonna give a proof of this, maybe we'll see. And but before doing that, I want to tell you about some theorems that could be proved using this lemma. So we will also see that this lemma is a corollary of a theorem of Emmanuel Breuillard. But okay, I'll tell something later about this. So yeah, so some. Oh wait, what happened? Oh, no, nothing. So here are like two new results that we get out of like this arithmetic Margulis lemma. So the first one is about like triangulations of this space X mod gamma. It says the following. It says that that there exist two constants C and D, such that for any arithmetic lattice, this lattice X mod gamma, this manifold X mod gamma, is homotopically equivalent. Here, actually, it should be homomorphic, but we got homotopically equivalent to a simplicial complex. So it should be homomorphic to a simplicial complex, where the number of the simplices is controlled by the volume. And the valence of each vertex is bounded by a constant independent of gamma. Okay, so basically saying that the volume is bounded like the complexity of these manifolds. So the idea of how to prove this is kind of simple. So if there was like some lower bound for like Margulis conjecture was true, and you had like universal lower bound in the system, what you would do is you take a lot of points, like a net of points where like the points are at distance at most E epsilon over 5, but at distance at least epsilon over 10, and then try to take a triangulation of this. And if you do this like in a nice way, you would expect that the volume of this would be related to this epsilon. And so the number of triangles or simplices that you need would be like volume of this over some constant depending on this epsilon. But because it's like this is not known, so we have to argue like in a different way. And the good thing for us is that we have like a very nice control on the volume of the thin part, what is called. So the thin part is where the injectivity radius of the manifold is very small. And yeah, so let me make a couple of remarks. The first remark is, well, maybe some previous results. First, so there was something that Gromov proved that is related to this, that is the following, that in variable negative curvature, you assume the curvature between 0 and -1, the Betti numbers are bounded by the volume. And this is a consequence of this, just because, you know, when you take the homology of this, the number of simplices is bounded by this, you would get this conclusion. And also, Gelander in 2001 proved this for non-uniform lattices. So our contribution is to the lattices that are co-compact, uniform. So
These are the Betti numbers of X mod gamma?
Yes. Oh, yes, thank you. Yes. Here's
So
X
these
mod
are
gamma.
just any for any manifold
But it's also,
of variable negative curvature.
yeah, it's also true for X, all right? Okay.
Yeah.
yes. But yeah. Yes. So Gelander proved it for non-uniform lattices, and Nikolai proved it for SL2. he actually proved.
They proved your result over here with the
Yes.
same simplicities.
Nikolai proved for the case where G is SL2R or SL2C. And he actually obtained much better results. He proved that these things are fatter than we proved they are. Okay, so the result is a bit better. Yes, so maybe I should make the remark that this is false for like groups that are not arithmetic. In H3, there is this thing called dense surgery, which allows you to construct manifolds with volume, infinite manifolds with volume bounded by, let's say, 1 million. Okay.
So false for non-arithmetic.
False for non-arithmetic, yeah. But it might be true in general. It might be something that is true for any lattice in Chen, where there are examples of non-arithmetic or a complex hyperbolic space. Okay. Let's see how. So I'll tell you about another result that we obtained with this. Is the following result: is that if you have a sequence of congruence arithmetic, so I would have to define what is congruence arithmetic. So like maybe like the example is you look at all the matrices in SL and Z, whose when you look at mod P is the identity. This would be like the subgroup of SL and Z satisfying this. This is a congruent subgroup, but it's kind of difficult to explain. So I'm not gonna say much more about the definition of what this is. But what we proved is if you look at the Betti numbers of these manifolds and divide by the volume, as the volume of the manifold go to infinity, then this converge toward this number that is called the L2 Betti number, that is really most of the times equal to 0. It's the fanciest way I know of saying 0. Okay, but we also prove something that is a little bit stronger. That is like that this convergence, if these gamma n's are defined over number fields with increasing trace field, then this convergence is a little bit better. Okay, and I just mentioned that. Yeah. So these results were proved by George and Wallace for when you take covers of a compact lattice and solving, I did prove the non-uniform case, I'm correct. And that is actually not a consequence only of our work, but it comes from work of like we have like a heavy input of work by a group of people known as the Seven Samurai. Okay, the Seven Samurai: Albert Bergeron, Breuillard, Gelander, Nikolov, Raimbault, and Samet. Yeah, so they prove this in the case where G has higher rank and property T, some special properties. But we got it more general, and yes. So there's also Nikolai who proved this for SL2, and Nikolai and Jean who proved this for. I don't remember, but they generalized this to another class of examples. Are there any questions? Yes.
What does Luke's theorem say?
So yeah, so I forgot to say that Luke's theorem is, it says that is when you have a covering of a specific manifold and you take coverings, and it's actually this result here. Yeah, so I forgot to mention.
Okay, so the first statement is just Luke.
Yes.
The shuffling equalities that
No, but these would have to be subgroups of the same.
Yeah, yeah.
It's be
Here,
random.
actually, the point is that these are not subgroups of the same group. These
Oh,
are
I
like,
see. Okay, sorry.
they are coming from different things. Yeah, yeah, and yeah, I should mention also that in the case where it comes from a simple, in the case where these are coverings, there are much better bounds. Like, for example, Mathilde, that was a graduate student here. I can't spell her last name. I think it's Gerbeli or Gigi. Mathilde Gigi. Like, she proved, like, for example, that this goes to a power. What? Gerbeli Gautier, yeah. So she proved, like, exactly like for some specific manifolds, like give like the exact rate of convergence, and the result is like deep, what it is for me, deep number theory. Okay, like endoscopy and something that I don't understand. Okay. So the tools in this theorem are well, these arithmetic Margulis lemma and something called like a Benjamin-Schramm convergence, which what it says basically is that a sequence of manifolds Benjamin-Schramm convert to another manifold if the part where if for every R you look at the manifold and you look where the injectivity radius is smaller than R, the volume of that, so this will be like the thin part of the manifold, is much smaller than the manifold. Okay, so this is so actually what we proved was this, that a sequence of manifolds converge Benjamin-Schramm to X. And like the proof of the seventh samurai actually used like a result of Zimmer. They use the stock Zimmer. So I said that because Zimmer is here. So yeah, I wanted to say this. But our result, yeah, does not. I mean, we don't use his result, but we still use like the fact that these lattices are arithmetic. So we're using Margulis superigidity. Okay. So these are two results, and I have 19 minutes left.
Sorry, but just I think
Yes.
So the main point is that you prove in these cases you get Benjamin-Schramm
Yes.
with even the better error terms by using that previous structure.
Yes, exactly. Yeah, and then like the seven samurai, like also an argument of the George and Wallace shows how to go from Benjamin-Schramm convergence to this statement. Okay.
What's the analytic trace formula?
Oh yes. So we, in the case where the manifolds, have degree like the. So this is like Nicolai's thesis. And so in the case where the degree goes to infinity, because of the arithmetic Margulis lemma, we can prove like that this manifold gets fatter and fatter. But when the degree doesn't tend to infinity, then we have to do another argument, and the argument uses like ideas of Nicolai involving the idyllic trace formula. So there's That's what I said. Thank you. And any other questions?
In that setting, when this degree is bounded, you end up having a fixed K? Even? Or
In that setting, we still have this. We still have this in the setting of the bounded degree, but we don't have any uniform like bounds on this because it comes from this notion of IRS. But yeah, it's not. Yeah, we don't get any bounds as far as I know. Okay, and then I'm gonna tell you a little bit about the proof, and the proof of this arithmetic Margulis lemma, or one proof, is related to a question that I really like. I'll tell you about it. It's about something called almost laws. So what is an almost law? So there's the notion of law in a group, right? So given a word in two variables, x and y, this word gives you a map from the product of the groups into itself, right? This is called a word map. And then a law is a word such that for all the elements, when you plug in the word, it gives you the identity. So for an abelian group, a law would be x, y, x minus 1, y minus 1, right? So what is an almost law is something that it tells you that it is very close to the identity. So it's a word such that when you plug any two elements of the group, you could be landing very close to the identity. So you might ask, which type of groups, can you make satisfy an almost law? And so I'm talking here because distance. I'm talking about compact Lie groups or Lie groups, but in the case of a compact Lie group, Andreas Thom, this is 2012 or 13, he proved that for every epsilon, there exists an almost law that takes the whole group into a neighborhood of the identity. And then, well, the idea of the proof involves this trick of, so taking commutators of commutators. As soon as you get something very close to the identity, then you have a word that takes things close to the identity. Then you take commutators of commutators somehow, and you end up closer and closer to as close to the identity as you want. And there is this question that I've been trying to understand is whether there is this almost law, but the question is, how fast can you make things go to the identity? So finding can you find a word such that always when you apply it to the group, you're exponentially close to the identity? So this question was a kind of what give a proof of the arithmetic Margulis lemma. So we were working with this with Homin Lee and Chen, and so we plugged some arithmetic matrices, and things didn't work out as we wanted, but we got a proof of the arithmetic Margulis lemma. So I'll tell you more or less maybe a 3-minute proof of this arithmetic Margulis lemma. Okay. So I'm gonna restrict to the case of GSL2R and gamma torsion free that correspond to just a surface, a hyperbolic surface. And here, this is the trace field. This is the degree. So as in example 3 before, this group gamma lies in SL2R, well, in this case it was SO21, but it's the same as SL2R, but times SO3 times SO3 K minus 1 times, and the K minus 1 times just coming from the other embeddings of the field. Okay, so there's like a natural map, natural group morphism from this group into this. And the idea is to show the arithmetic Margulis lemma is to take, okay, suppose I have these two loops, X and Y, and I want to show that this orange string is long. So I take the matrices corresponding to this and apply the word to that. So the word was like some word here, X squared, let's say, and my Y squared, whatever. It is doing something. But this is when you look at this embedding here in SL2R. But when you look in the SO3, this has to be very close to the identity. So here it has to be very close to the identity. And that implies somehow, because like the entries of these matrices are, so when I take, okay, this is like a really long equation, but what I'm taking is the word minus the identity. So when I look at these places, this is going to be very small. But then when you take, for example, the trace and multiply over all the embeddings, this has to be an integer, because all the matrices were arithmetic. So this has to be an integer, and then it's an integer whose product, like in this side, is very, very small. So that implies that in this side is like really, really big. Okay, so it comes from this trick. Like if you have an algebraic number, algebraic integer, and you multiply all the conjugates, it's a positive, so it's a number, it's an integer, and so it's greater or equal than 1. But if you know most of the factors are very small, then there should be a really big factor. And so the proof boils down to more or less that. Yeah, so I have 9 minutes left. So I could give more details to the proof, but I think I'll just leave it there. And I'll mention just something about like a connection to like a theorem of Emmanuel Breuillard that is called kind of a non-abelian version of the what's the name of like this Lemmer's conjecture. And its statement takes it requires some definition, so let me try to give it. So here I'm taking a set of matrices, so just a finite set of matrices, say 2 matrices, and all the matrices, the coordinates are algebraic integers. And then for a matrix, you can define what is the height of the matrix. That is very similar as what I defined for like a number. You remember for a number was log plus of this. So what you take is you sum the norms of this matrix in all possible embeddings of this matrix in completions of the field K. So in the case where the matrix was just like the entries are algebraic integers, it's just the log of the norm plus the log of the norms of the conjugates. So this is just like the conjugate of this. Oh, looks really bad. This is minus square root of 2 plus 1. It's just conjugate of this. And you sum these logs. And so that's the height of a matrix. And then what's the height of a set of matrices? Just the maximum of the heights. And then there's this other forget about this. Okay, this is a like a normalized height that is just taking the limit of f to the n over n. But for simplicity, just let's focus on the height of f. And so what Emmanuel Breuillard proved was that is the following theorem: is that there exists some epsilon such that for any finite set of matrices, either the group they generate is virtually solvable. So that means it's a very easy group to understand algebraically, or the height of this height is bigger than epsilon. Okay, so it's telling you that if a group is not like an abelian or solvable group, you somehow can generate elements like in a fast way that have very large norms. And yeah, so using this trick of the almost law, we were able to like reprove this theorem. So this theorem also implies this arithmetic Margulis lemma. And oh, I forgot here. There's here a normalization of 1 over. Oh, I made a mistake here. There's a normalization here. I have to divide by the degree of this field. But okay, we obtain a new proof of a very kind of short proof of this theorem using the idea of almost laws. So that's all I wanted to say. Yes.
So you mentioned Benjamini-Schramm convergence of various kinds of manifolds.
Yes.
So I've seen this in like, this concept comes up a lot in probability, and it's usually a mode of convergence of graphs.
Yes.
Right. So how is that mode of convergence of graphs related to this?
So it's just like a generalization of that fact of graphs, like so it's a generalization. So there's kind of a in graphs you have somehow what you take is like a measure of pointed graphs, right? That have a specific point. So when you're looking at one of these manifolds, x mod gamma, this gives you like a probability measure on pointed manifolds. So like maybe yeah, well I don't have a picture to explain it, but just basically if you have like the G mod gamma, right? You take a point here and then you look at the manifold from this point. So this gives you a kind of the manifold itself gives you like a probability measure in the space of pointed manifolds. So you have to think of the space as a probability space where each point is not just a point, but it's how the manifold looks from that point. It's the same as in like graphs. And then you study this, so this corresponds to some probability measure. And then you look at how these things, the possible limits that these manifolds can take. So this was like the x mod gammas. And these manifolds converge to some object, and so you try to understand these possible limits.
So is it saying that somehow like the local topology of the manifold near that point X is converging?
Yeah, I mean, what is actually happening is like very simple, because it's like basically for in our example, because this was converging to X, what it's saying is that like around every point, most of the points. The manifold, if you look at a ball of big radius, you know, the points where it doesn't look like a ball, like here, you don't see them very often. It has very small volume. So most of the manifold just looks like the whole big space.
It's fat.
It's fat. Yes, exactly. Yes. Yes.
And could you also just point out exactly where, obviously you're using an arithmeticity. So
Yes,
where's the key point?
Oh, yeah. I mean, so it's in the arithmetic Margulis lemma. Like the proof that I gave was that this quantity is bigger than 1, basically. Okay, it's just this is comes from some arithmetic.
I mean, like, so for any lattice, the entries
Are algebraic.
are algebraic.
Yes.
So
Yes. So, but this wouldn't give you something that is greater or equal than 1. Okay, this might give you a very small number. So you can.
just because I mean, because they're actually using the integral rather than just.
Yeah. I'm using the fact that they are integral.
Okay, so you could replace arithmetic by ones, which is sort of S integral, or maybe an integral to something.
Yeah.
Because I mean, an integral might be slightly weaker than arithmetic.
Yeah, I don't think we haven't been able to get anything better than this. I mean, yeah.
But yeah, you're literally just using. I mean, here you're using that this quantity is an integer.
It's an integer. Yes, it's an integer. Yeah.
Are there any more questions? Okay, so let's thank Sebastian again.